All right, back from break. Let's take a look at the rest of Chapter 2. So far, I hope things are going well with this. We've looked at displacements, we've looked at velocities, and we've looked at accelerations. And those are the big three players here. And of course, time, everything in terms of a function of time. So here's another example, and you'll see that they've got these automobiles going on here again. So here's an object. It says that we have, this car is going to be accelerating at 2 meters per second per second. It's going to start at a location which we are going to designate as 0 meters. So it sounds like that's the origin of our coordinate system. So we're going to say, why not? Let's let the car be right at the origin of the coordinate system here. And it's also going to be starting at rest. So x naught, that's how we say it. The little 0 off to the side, we call that a naught, as in N-O-T. That's how it's pronounced. It just really means a starting number for that variable. So our starting value of displacement, x naught, is 0. Starting value for our velocity, v naught, is also 0. We're starting from rest. Now it says what happens is a light turns green and the car takes off. And it takes off with an acceleration of 2 meters per second squared, and that's a constant value. So the acceleration remains constant all the way across the intersection, and it says that the intersection has a width of 30 meters. That's a pretty good sized intersection, right? 30 meters is a good long distance for an intersection. Okay, so the question is, how much time will it take? How long does it take for the car to cross the intersection? Now we got to be clear about what we mean by this. So at this point we're not trying to trick anybody, but notice the way they've got this set up, and I think this is the right way to do it. They've labeled the front of the car as the point that we're keeping track of. So they're saying that the front of the car will have traveled a distance of 30 meters across the intersection, but notice the car is not out of the intersection yet. It's still kind of in the intersection, but we're going to ignore that. I'm not going to worry about it. So I'm going to say, okay, here is, I'm going to call it distance d. I'm going to call that 30 meters. I'm going to say the car is going to, this is given. So these are the given pieces of information along with, this should be up with the given, x naught equals 0, v naught equals 0. What they want us to find is how much time does it take. And they're telling us that, so this is more given stuff here, right? And this is what we want to find. That's a lot of information given. Now here's the car when it's starting off, and here's the car when it's traveled the 30 meters. I'm not going to say whether it's out of the intersection or not. These are the formulas for constant acceleration. Now I would like to be able to use those, but I can only use those if the acceleration is constant. And so I have to verify that that's the case. They did tell us that, right? Constant, there it is, there's the word. See, I read the problem carefully. Constant 2.00, 3 significant figures, meters per second for the acceleration. So I do get to use these formulas. Now there's 3 of them. Do I use them all? Which one is it that I want to use? And for that, I'm going to look at the information that's given. First of all, x naught is equal to 0, v naught is equal to 0. Zeros can be very good, because what that says is this equation simplifies a lot, and this equation simplifies a lot. Look, that drops out, that drops out, that drops out, that drops out, that drops out. Lots of stuff drops out of the equation, given that x naught is 0 and v naught is 0. And then x is equal to 30. So I have x naught. I don't know t. But I do have the distance. So let's do this. Let's take this equation, because I have the x's. I don't have the velocity. Well, I have the starting velocity, but not the final one. I have the x's before and after, and I want to find out how much time. Now, that equation simplifies to this because x naught is 0 and v naught is 0. So now it's a much simpler equation than it was over on the left side. And this equation can be solved for t. If I solve this equation for t, that's going to give me 2 times x divided by a square root. And just to let you guys know, all my square roots I write as to the 1/2 power, which I'm assuming you guys already know that, but so watch for that when you see these 1/2 powers. Plugging all the numbers in, I put a 2, I put in my 30 meters, and then I put in my 2 meters per second per second. Those are the units for acceleration. And you know, before I even get the calculator out, I'm going to check units. Because if the units don't work, what's the point of doing the calculation? Something's wrong unless the units have correctly canceled out. In this case, the meters on top cancel with the meters below. That looks good. I have 2 powers of seconds in the denominator of a denominator. Now, denominators of denominators end up in the numerator. So I've got 2 powers of seconds in the numerator, and then I'm going to take a square root. It says that my units should work out to be seconds. So the units are going to work out fine. The units are looking good. So there's a good chance I've done this right. So I'm going to put the numbers into 32, square root all of that, and it says it's actually going to take me 5.48 seconds to get across this intersection. That's like 1, 2, 3, 4, 5.5. Yeah, it's a pretty good sized intersection. Maybe I need a little more acceleration to get across. But anyway, I think we successfully solved this. Now I want to ask a couple more questions. How fast then will the car be moving once it has traveled the 30 meters? So what we can do now is, now that I know the time, I can come back and use the other equations. I just want to practice the other equations. So what I'm doing is I'm coming up to here and saying, now that I've solved for time, I could solve this and find out how fast I'm going to be going. Now remember, the v naught's just 0. And then this equation, how could we use this? Well, that one also we could use to calculate how fast we're going. Maybe we can do both and see how the answers compare. So I used equation number 1, plugged the numbers in, and I got 10.95 or 11.0. I rounded back to 3 significant figures. When I used equation 3, oh look, I got the same thing in any case. So, you know, it's like doing a puzzle, right? You got to get those first pieces in, and then you can see that the remaining pieces, there's only a few places they can go. Is kind of how this is all working. All right, what about, braking distances? How much distance will be required for this car to slow down and stop? Looks like it's out on the Utah Salt Flats or something, right? Racing along here. Let's see, so we're going to start with a velocity of 14 meters per second. And, they did complicate the problem. Look at that. There's a reaction time of a ½ second during which the car continues to move at a constant velocity. So what they're actually asking is not how long does it take the brakes to stop the car. They're saying once the driver realizes they need to stop, how much distance are they going to cover? So let's break the problem into 2 pieces. Let's break it up into one section where we're traveling at a constant speed during a ½ second of reaction time. And then the second part of the problem is where we're actually slowing down. We put on the brakes and we experience a deceleration. They tell us the deceleration. Okay, it looks like the information is here. So it says that we're going to decelerate from 14 meters per second to 0, and the acceleration is going to be 6.0 in the direction opposite to the velocity. So the direction of the acceleration. So here's some graphs. I love graphs, I have to say that. So v, as a function of time, during that first ½ second, the velocity stays right at 14 meters per second. So the brakes have not been put on. The driver's just going, huh? What? I need to put the brakes on? And so for a half second, the car continues to travel at that speed, and then the brakes are engaged, and it's a constant. I hope they told us it was constant, right? We better go back and read that. But so for a constant deceleration, that's going to be a straight line path on a velocity versus time graph. Now, what's going to happen? And they told us, what was the other part they told us? Oh, they told us the acceleration, right? Okay, now the x is going to be different. For the first half second, the x is going to continue to increase in a linear fashion. And then, once the slowdown begins, then the slope of the line needs to drop off. That actually turns out to be a parabola. So it's a straight line with a slope of the velocity for the first half second. And then it connects with a parabola. So let's see what the numbers work out to be. Here is the constant velocity part of the problem, where the accelerations are all 0. X naught we're going to call 0. The velocity is 14 meters per second. The time here is 1/2 second. So we traveled 7 meters before we ever got the brakes put on. So 7 meters before the brakes went on. What about this, once we put the brakes on, once we do have an acceleration? Now, this is the formula that I pulled out. Now, why this formula? Notice that that's the formula that doesn't say anything about time. We weren't given any time information, and they didn't ask us to solve for time. And so what they did ask about were stopping distances and velocities. So this is the equation. Let me go back very quickly, because I want you guys to get familiar with these. Anytime the acceleration is constant, oh, it's farther back, isn't it? There it is. These are the 3 equations, right? The 3 equations. And there they are again, right here. So the 3 equations are right here when we looked at that other example. And now, okay, so I used equation number 3. I put in the x naught is equal to 0, and I put in the acceleration of -6. I put in the starting velocity, this time is 14. It's the ending velocity that's 0. So I solved that equation for x, put everything in algebraic form, and then I started substituting in the numbers. And I think that's the best approach. Don't put numbers in right away. I would not put numbers in. I'm going to encourage you not to put numbers into that formula yet. I would say look to see if anything is 0 and can just be canceled out. Something is 0, I can just drop this. And then do the algebra to this point. If I use the algebra, I can still look at that and ask if that formula makes sense. If it's a bunch of numbers, I don't know what the formula is really telling me. So do the algebra first. I highly, highly recommend that in terms of learning physics and becoming more proficient at problem solving. Do the algebra first and then put the numbers in. The answer that I ended up with was 16.3 meters. So I have to take both parts of the problem, I have to add them together. There was 7 meters before I got the brakes on, and then over here it's 16.3 meters to stop the car. Now the acceleration was -6 and the speed we started at was 14. It's going to take, a little over 2 seconds to slow the car down, but that's something else you could go in and calculate. How much time did it take to have the car slow down? Okay, so that's the total distance that this car took to be able to slow down. Oh, I did do the stopping time. There it is. So I went back and used equation number 1, plugged all the information in. It worked out to be 2.3 seconds for the car to come to a stop. All right. So let's move on from just kind of a general category of constant acceleration. We want to look at a very special category of constant acceleration, and that would be objects that are falling in a gravitational field. So near the surface of the Earth, Earth's gravitational field creates, as you get closer to the Earth, the gravitational field creates a larger force and a larger acceleration on objects. But for an object that's being dropped over a short distance, we can treat that gravitational field as if it's uniform and constant. Okay, so it's a bit of an approximation, but over short distances, that's going to work fine. So again, near the surface of the Earth, gravity creates almost the same, approximately the same acceleration for all objects. And so this is one of the most common examples we can use and use constant acceleration. Again, it's because we're staying close to the surface of the Earth, we're not getting very far away. So in the absence of air resistance, everything falls together. Now, you know, when we say everything accelerates at the same rate, clearly they don't. A leaf falling off a tree does not fall like a brick, right? So why would they tell us this? And the idea is, oh, it's in the absence of air resistance. It's with all other forces removed, gravity by itself causes everything to accelerate at the very same rate. So everything will have the same acceleration if we get rid of the atmosphere. So you could think about doing these experiments on the moon, for example. If we were on the moon, oh, there's no atmosphere there, then everything drops at the same rate. So if you take a feather, and you take a leaf, and you take a brick, and you let go, they all accelerate together. They all drop at the same rate. So what are these pictures showing us here? So here, the paper has a lot of air resistance, and as a result, that's reducing the acceleration. The air resistance creates another force acting on the object. Now what the person has done here is crumple up the paper to not eliminate, but to highly reduce the air resistance, and now they're dropping much, much more similarly side by side. Okay. So air resistance complicates things. Just think, if there were no air resistance, everything would be dropping like a brick in the autumn. You know, when the leaves fell off the trees, those leaves coming off those the high branches, those would be hitting the ground at 100 miles an hour. Raindrops would come in at hundreds and hundreds of miles an hour. It would be dangerous in a rainstorm if we didn't have air resistance. So here's an example that often gets used, and so maybe you've seen these examples in videos. Here is a tube filled with air, and here is a feather, and here is another object inside here. If we now remove the air and drop them again, we can see that with the air resistance gone, the feather now drops like a brick, just side by side. All right, let's try some freely falling examples. Here is a freely falling example. Here it looks like the Tower of Pisa, right? So here is the Tower of Pisa. It's leaning. Apparently it's been stabilized now, though, so it's not going to tip over, although I'm not sure if I want to stand right there. So what it's saying is this. Suppose that we drop an object. It says a ball, but I would go with something dense. A block of iron or something, a brick or something like that. Anyway, we're going to drop a ball from rest. From, I think they got is that a V? I guess it is. Looks like a Greek letter. So the V here, the starting velocity is 0. The tower is 70 meters high. How far will it have fallen after 1 second, after 2 seconds, after 3 seconds? And there's the key item, ignore air resistance. So I'm going to ignore air resistance on this one. Here we go. So here is the object. See how well I drew that? There is an acceleration. And here is the formula I want to use, because what they said is, as time goes by, how far will the object have dropped? Now, you might say, but wait a minute, isn't this the y-axis? And I just like using x. it's still a one-dimensional problem, so I'm going to stick with x, at least for right now, and just continue using x, I think. So we can say x naught is right there, and I'm going to go ahead and call that 0. So remember, we get to fiddle around with the coordinate system and set them up however we think it's going to be most useful. And in this example, if I set x naught to be 0 right here, notice that all of the displacements, all of the velocities, all of the accelerations are downwards. Well, I'm going to go ahead and call that the positive direction. So I'm going to say down is positive. I wrote it right there. Hey, this is x equals 0, and this is the positive direction, not just for x, but for velocities and accelerations. Now, the acceleration that we get from Earth's gravitational field near the surface is 9.80 meters per second per second. So that's, we can treat that as kind of like a constant that we use if it's Earth's gravitational field near the surface. So that's a number that we'll use very, very frequently. Now, I can bring in my other formulas for constant acceleration. V naught plus AT, x naught plus V naught t plus 1/2 AT squared. So there are the equations that we've got. Now, since x naught is 0 and V naught is 0, because it starts from rest, this one I chose the coordinate system. This is because they told me it's starting from rest. Now, that drops out those terms, and again, we've got that lower equation reducing down to be 1/2 AT squared, where A is the acceleration due to Earth's gravitational field near the surface. So I'm just going to keep plugging into that equation. What I'm going to do is, if I put 0 in for t, I'm going to get 0 for x. That works. If I put 1 second in, I get a velocity. Oh, where's my velocity? There it is. My velocity formula is here. I didn't bring that one over. But the V naught is also 0. So V is equal to A times t. So this is just A times t. This is 1/2 AT squared. So after 1 second, I'm going 9.8 meters per second. After 2, I'm going twice as fast. After 3 seconds, I'm going 3 times as fast. That's what constant acceleration behaves like. So the velocity is just steadily increasing. Now, what about position? What about displacement? So during the first second, I have traveled 4.9 meters, but look, I've traveled farther between the first and the second mark, and then I've traveled even farther. Why is it that I just keep traveling larger and larger distances? And that's because I'm accelerating. If I were going at constant velocity, all those intervals would look the same, but I'm not going at constant velocity. This object is accelerating. And so the distances then, you can see that they're getting larger and larger. All right, that's it. That's what they wanted, is to know how far this object would have traveled at these times. We should have done some graphs on these too. Let me see if I had, no, I did not have the good sense to draw some graphs. Draw some graphs on this. What you're going to find is that this formula is a straight line. V naught's equal to 0. So that's a straight line, V versus t, where the V just increases steadily. But this is a parabola. So x, as a function of t, that's going to have this parabolic shape to it, and x is going to be increasing faster and faster because of the acceleration taking place. Okay, what if we go back to the very same tower? We're going to drop this again, same deal as before, except we're going to give this an initial velocity downwards. We're going to pick this thing up, we're going to throw it down. That's going to get it to speed up. Now, what would its position be, and what would the speeds be after 1 second, and then after 2 seconds, and then compare it when we just drop it. Now, we can already look at the formulas and see how throwing it is going to affect the velocities and the displacements that we've got. So here are the formulas. I brought in 2 of the constant acceleration formulas. These are the ones that have t v is a function of t, and x as a function of t going on. And let's see then, what's happening here is that I'm going to have an initial velocity of 3. Before I didn't. Now, what effect is that going to have? Well, all my velocities will get bumped up by 3. So now my velocities start right out at 3, and instead of 9.8, I have 12.8. Instead of 19.6, I have 22.6. Instead of, what was that, 29.4, I have 32.4. So what's happening is I have an additional 3 meters per second at each of these times that we've calculated. So that gives me an additional steady 3 meters per second in addition to what I would have had otherwise. Now that's going to show up in terms of displacement. So that means that every second that goes by, I'm going to have traveled 3 meters more. So because of that initial extra 3 meters per second, I'm going to have this extra term right there. And that's just going to keep giving us an additional 3 meters each second that goes by. And so with that in place, I'm getting 7.9, 25.6, and 53.1. And notice, compared with what we had before, this was an additional 3 meters. This is an additional 6 meters. And this is an additional 9 meters. So yeah, I'm picking up that extra displacement. And that's got a time factor in it, so as time goes by, it's giving me an additional 3 meters every second from what I would have had if I had not thrown it down with the additional 3 meters per second. Okay, that seems all right. So let's look at freely falling objects again. Now, we looked at this example before. I think it's worth coming back and taking another look at. So we have a person here. This person has thrown the ball up. Now, remember, the formulas that we're looking at are not describing how the person threw the ball. What they're asking is what happens once the person lets go of the ball. So point A doesn't mean it's in her hand. Point A means that she's let go. So she did a big wind up and began throwing that ball upwards and then let go, and that's point A. And that's when we start the timer, and now it's going to go up. It's going to have an initial velocity of 15 meters per second. That's pretty good. So that's, she's throwing this up in the air at like, what is that? That's like better than 30 miles an hour? And she's just doing it, I mean, she needs more of a wind-up, right? So anyway, she launches this up at 30 meters per second, and then it slows down, it momentarily comes to rest at point B, but then it picks up speed due to the gravitational field, which is shown here. So the acceleration is determined by the gravitational field, and comes back down to point C. So they want to know how high does it go, and how long is the ball in the air before it comes back down to point C. And it's going to come down at 30 miles an hour, so the person better be ready to catch it. All right, let's see. At point A, we're going to call that x0 equals 0 meters. We might as well use that as the start of the coordinate system. And the initial speed is 15. Now when we get to point B, we don't know how high it's gone, but we know the speed has dropped to 0. So let's use equation number 3 from the list of constant acceleration formulas. So I'm going to bring out equation number 3 because right now they're not asking anything about time. That's later. So for right now, we just want to find out how high it went, and this equation will work. So what I can do now is I can set v equal to 0. I'm going to set this side equal to 0, and then solve this algebraically. Now I'm solving for x. And that brings a minus sign here. Now that's always interesting. When I get minus signs, are the minus signs going to be telling me something? Because I better keep track of all the minus signs correctly. So this becomes minus v0 squared over 2a. and then, so this is minus 15 meters per second squared divided by 2 times, that's the gravitational field or gravitational acceleration. And the minus signs canceled. So I did actually have the minus signs cancel on this one. I'm getting an x value of 11.5. I should point this out too. We saw that picture before. Since this thing is being thrown up, on this problem I'm going to go ahead and use upwards to be the positive direction. So that means that the x values should all turn out to be positive. Now the v values, the initial velocity is 15, and that's plus, because we're saying upwards is positive. That says on the way up, v should work out to be positive, but on the way down, v should be negative. And then a is going to be negative the gravitational field, or gravitational acceleration, and g itself does not have the minus sign. I have to put the minus sign in. G itself, little g, is defined as 9.80 meters per second squared, and that's the gravitational acceleration, or we're going to find out it's the gravitational field of Earth. So that is Earth's gravitational field at a location near its surface. And that's why it's little g. So we got the height figured out. This thing is, it's a good distance, right? It's going to go up 11.5 meters. So meters like this, it's going to go up, you know, like to a 3 or 4-story building. Now they want to know how much time it's going to take. Now, going up and coming all the way back down in terms of time would require me to use, well, I could use this equation, but it could turn out to be a quadratic. What I've done is I've broken the equation up. You don't have to do it this way. You're going to find that there's different paths you can follow in solving these problems. But what I'm going to find here is that I've decided to break this up. So going from A to B, I'm going to say V is equal to V naught plus AT. I'm going to find out how much time that takes, and it's 1.53 seconds. So it takes 1.53 seconds to go up. Now I'm thinking that everything we've learned so far suggests that, you know, whatever the rate of slowdown on the way up, that is duplicated in reverse order on the way back. And so I'm thinking that kind of suggests it should take the same amount of time to come back down. Now that's ignoring air resistance. So remember, air resistance is being ignored here. So if you're going to try this on your own, you need to use like a baseball. Don't use a feather or a leaf. Use a baseball, something like that, to try this out. So it's taking 1.53 seconds to go up. Now for the way back down, I decided to try a different formula, just to see what would happen. Now in going from B to C, I'm going to reset x naught to be equal to 0. So when I break a problem into pieces, I can redefine my coordinate system. So now I'm going to treat this as if the ball is just being dropped from rest. And we've looked at that problem before. We've used this equation, and I've actually switched the direction of positive. I said, okay, for this part of the problem, I'm going to say downwards is positive, because I'm starting at that top point, coming to my lower point. And again, you're going to find when you do these problems, there's different ways to work through the problems and get them to work. Okay, so let's see what happened here. For this new coordinate system, x naught is 0, v naught is 0, I can solve the remaining equation for time, do the algebra first. Now that I've got my time figured out, I can start putting numbers in, and it worked out to be 1.53. So it turns out algebraically we can show that if gravity is the only effect, that's the only force acting on these objects, that the time it takes to go up will match the time it takes to come back down. So now we can use that in a problem when we break the problem up into different pieces. Okay, more examples. I think that's kind of the rest of the chapter is working some more examples. We're not through yet. But this is saying conceptually there's two possible misconceptions going on here. Let's see if that applies to us. The first common misconception is that velocity and acceleration have to be in the same direction. Now, think about that. We've shown in several examples that v and a can be in opposite directions, or they can be in the same direction, right? Either is a possibility. If v and a are in the same direction, the object's speeding up. If they're in opposite directions, the object is slowing down. Now, the other misconception they list here is that an object thrown upwards, right at that top point where the object momentarily stops, where the velocity is 0, that the acceleration goes to 0 at that point, and that's not true. That's like saying when the object gets to the top and momentarily stops, we turn off gravity. And if we did turn off gravity, if the acceleration really were 0, and the gravity had been turned off, the object would just hover. So the fact that it continues and comes back down tells us, nah, the acceleration didn't go to 0 at that point. All right, so let's try this again. So we're going to throw the ball back up in the air, and this time, let's consider making some more calculations. So what we want to do this time is find out how much time it's going to take for the ball to reach the max. Did we do this? And the velocity of the ball when it returns? We might have been overachievers and already solved for this. Oh, well, in any case, I left out the solution. I think we already solved for all of those. So we were just ahead of the game here. Okay, so the velocity of the ball coming back down, I guess we didn't solve for that. If there's no air resistance, then we can use that same argument as the rate at which the ball slowed down on the way up is going to match the rate of it picking up speed. If it was thrown upwards of 15 meters per second and there's no air resistance, it's coming back down at 15 meters per second when it gets to the same elevation. So when it gets to that same elevation with the thrower's hand, it's going to be right back at the same velocity as when it was launched. All right, so let's look at a graph. Graphs are great. I know I keep saying that, but I want graphs to be your friend. This is x. I know they wrote y, but I'm going to say this is x. So this is the height as a function of time. And so we calculated the times. It was 1.53 seconds to the top and an additional 1.53 seconds to come back down. So we did get all of that calculated. And now what they're saying is, they're going to give us one more problem here. Calculate the specific times when the ball passes the height of 8 meters. So we know that the ball is going to reach all the way up to 11.5. It's going to pass the 8 meter mark on the way up. It's going to pass the 8 meter mark on the way back down. Let's find out at what times that's happening. Now, this was the graph that we had alluded to before. We mentioned these are some nice graphs to stare at and think about, because what we're seeing is x as a function of t is this parabola function, and v as a function of t is a straight line, and that tells us the acceleration is constant. The acceleration is constant, so the velocity is a straight line. All right. Now, we want to get about looking at this. Let's see, we've played around with these formulas a fair amount. I'm hoping we're getting to be more and more familiar. We can do this, right? Let's see how this might work. Oh my gosh, look at that. I can't believe it. I used y. Okay, that always makes me a little nervous. I know this sounds crazy, but when I'm using x as a variable, I have a higher success rate than when I use y. I don't know if any of you have that same issue, but you have to realize I'm out on a limb here using y for this. Anyway, so I'm going to bring out the y as a function of t, and because that's what they talked about, right? Was how much time, at what time t, will the ball cross the 8 meter mark? And we saw from the graph, it's going to happen twice. Once on the way up, once on the way down. So why not, we're going to say is 0. And the y we are interested in is 8 meters. So I can plug those in. The initial velocity is 15, so we're back to saying upwards is positive. Upwards is positive. G is equal to 9.8 meters per second squared, but what that tells us is, here we go. Y is equal to y naught plus vt plus 1/2 at squared, but since the acceleration is negative g, I put the negative sign here and I put the g there. All right, and g is Earth's gravitational field near the surface, also known as the gravitational acceleration. So this formula, now I got a 0 here, that's good news, but that is not a 0. And so I'm left with a quadratic. Now, I'm okay with quadratic. Quadratic can actually be kind of interesting to solve for. And I intentionally do want to solve this using a quadratic, so we can talk a little bit about setting up quadratic formulas. So what I did was I brought the t squared term to the front, and I gave it a plus sign. And then all the other signs had to match accordingly. And I ended up with this quadratic formula. So that's a quadratic formula. It's a function of t. And so t is equal to minus b over 2a. Now b over 2a, minus b over 2a, the minuses cancel. I'm left with v naught over 2 times 1/2 g, and that's just a g that's left over. So t is equal to v naught over g plus or minus b squared minus 4ac square root over 2a. Now you guys are saying, I know, that can't we just combine them with one denominator? And I'm going to say, yeah, we could, but we're going to learn something by setting it up this way. And that is often, very often in physics, when we're using the quadratic equation, this number is going to be meaningful by itself, and then plus or minus here tells us that the solution is, the two solutions are evenly spaced surrounding that central number. Well, the central number here is 1.53 seconds, if I take the v naught and divide through by g, plus or minus 0.84. So what this is telling me is that the two solutions that I'm looking for are evenly spaced between that location. So this is the 1.5 seconds, and then if I use the plus, I get this solution. If I use the minus sign from the quadratic, I get this one. So the two solutions can be looked at that way. And so it would be, and there's everything. You're still going to have to get all the numbers put in and make sure that you can successfully use your calculator to get these numbers. But this is 1.53 plus or minus 0.84. That says on the way up, it crosses the 8-meter mark at 0.69 seconds. On the way down, it crosses at 2.37, and those two times are evenly spaced around 1.53. All right. Oh my gosh, is this our last example? So this time, we're at the edge of a cliff. And I think we're getting close to this. So we're at the edge of the cliff, we're going to throw this ball up. See, we've done this all with those constant acceleration formulas, just to point out. I'm going to throw this up, it's going to go up, it's going to slow down momentarily, stop, and then it's going to drop all the way down here. Now what they seem to be suggesting is, y equals 0 is here. That's going to be y equals minus 50. We're still going to be throwing this up at 15 meters per second, but now the person walked to the edge of the cliff in order to do this. Now what they want us to calculate is what's the total time this object is going to be in the air. Now I'm going to tend, we could use one equation right here, that would work, try it both ways, but I'm going to break it into two pieces. I'm going to find out how much time it takes to go from A to B, and then from B to C. Now notice B to C is longer than A to B because C is much farther now. It's not coming back to the same elevation, it's dropping 50 additional meters. So anyway, I'm going to use two steps. So I'm going to break this into A to B. Now for A to B, I can say that y naught is 0, v naught is 15 meters per second, v is equal to 0, And so here's A being solved down here. So the A stuff is down here, the B stuff's up there, B to C. So I'm using this formula, B equals V naught minus GT. And since V is equal to 0, this simplifies to the amount of time, and I'm doing this all algebraically, right? I have not put numbers in yet. So I've done algebra all the way up to this. That's V naught over G, which is what we saw before. 15 meters over 9.8 meters per second. Well, we're getting the same answer. We threw it upwards at the same speed. It's still taking 1.53 seconds to reach point B. Now, coming down is going to be different. So let's think about this. On this one, y naught is equal to 0. So we're redirecting our coordinate system so that downwards is positive. And so y naught is equal to 0, v naught is equal to 0, and that reduces to 1/2 at squared, where a is equal to g. So this is the height we're going to drop from. Remember, we had solved this earlier. I guess I'm going back and using that, huh? So the total distance this is going to drop. Remember, this went up to a height of 11.5. On the way down, it's going to go through the 11.5 plus the additional 50 meters, and so that's where I'm getting the 61.5 from. So this becomes 61.5. I plugged all the numbers in. I'm getting 3.54 seconds for the way down, added to 1.53. The total time works out to be 5.07. Okay, so I hope this is fun. I hope you're gonna impress your friends with this stuff, right? You're gonna be able to impress your friends. Now, as far as distances traveled, on the way up we got that 11.5. We had done that problem earlier. So same as before, what we're going to do is use equation number 3, which relates distances with velocities. And v naught is equal to 15, v is equal to 0, y naught is equal to 0. A lot of stuff drops out. I do the algebra first, plug the numbers in, check the units. Meters squared divided by meters leaves us 1 factor of meter. Here I have 2 factors of denominator in the denominator of the numerator, and here I have 2 factors of seconds in the denominator of the denominator, and the denominator and the numerator and the denominator, those are going to cancel. So the seconds all cancel, the units check out, and we're getting 11.5. Now we did it before, that's what we got, so we're thinking that's looking pretty good. So it went 11.5 meters up. On the way back down, it went 11.5 plus 50, so the total is going to be, total distance traveled is 73 meters. There we go, summary of chapter 2. I knew we could do it. Let me know whatever questions are coming up. So we're into the real physics now. This is kinematics. This is going to stay with us. We're going to keep doing these kinds of kinematics calculations for the foreseeable future. So if you guys have questions on anything, stop by office hours and let's get those looked at.